Good afternoon, folks. Welcome to this afternoon's session all about the ArcGIS Runtime and Analysis. So we'll be looking at all of the different analytical capabilities that the ArcGIS Runtime allows you to implement in your custom applications. So the first thing to talk about is just a quick look at this slide, which essentially covers the cross-runtime sessions that we're running at the DevSummit this year, all about the runtime. And it mirrors the way that we actually build the ArcGIS Runtime. So the common core code base that we build all of the ArcGIS Runtime SDKs from allow us to implement a common API design across all of those runtime SDKs. And that lets us host a series of sessions, such as this one about analysis, that apply across all of the different ArcGIS Runtime SDKs. So the .NET, Qt or Qt, Java, Android, iOS, and macOS. Everything that we're talking about today is relevant and available in those SDKs, and we'll highlight any cases where it might not be in case of platform support. And then the list of sessions there, that's kind of for reference. So the slides will be available to you after the conference, and those are a series of recommended sessions that are worth watching the recordings of and downloading the slides for. And then in the case of each of the SDKs, there's a product-specific session as well that will be covering, going into detail about those specific APIs or platforms. Okay, so in the session today then, we'll be looking at the different analytical capabilities, so covering the geometry operations that you can perform on fine-grained geometries as part of your analysis workflows. We'll take a look at geoprocessing and how that is realized and utilized within the ArcGIS Runtime. We'll look at analysis tools and visual analysis as well, so some of the new capabilities that were actually just released in the very latest release of ArcGIS Runtime, and then we'll have a summary and roadmap to wrap up at the end. So first of all, I'll hand over to Mark to talk about geometry operations.
Switch over. Okay, so the geometry operations we're talking about here are all methods that are all contained inside a class called the geometry engine. And it's available for all of the runtime SDKs, be it desktop or mobile platforms. The class contains lots of static methods for, well, as the name might suggest, geometry. So by geometry, we're talking here about points, lines, and polygons. And these are the geographic representation of the features you may have in a feature class, or the graphics that you may display as temporary information in your applications. Now, the geometry engine is all about client-side processing, so this is all carried out on the local CPU of the device. So that actually makes it very quick, because we're not going off to a server to request the results. And it also means that it's actually very good for big bulk operations. So if you've got lots of operations to do, then it's obviously naturally very quick to do it locally on your device. Now, the geometry engine contains sort of a huge number of methods. So to try to break this down, I've broken it down into three main groups of functionality, which I'll explain. So the first of which is around geometry dimension questions, and then we can look at the geometry spatial questions, and then there are a group of methods in there that enable us to be able to build up new geometries. So I'll start off by looking at the geometry question. So this is where you can work out something like how long is a line. We might want to work out the area of a polygon, what the boundary of a polygon is. So you might want to answer the question, how much fencing material do I need to use to put around the perimeter of a field? Or it might be something really simple, like just what is the distance between these 2 points? So I'm just going to show you a little bit of code samples here. So I'm looking here at a piece of Java code, which is using the distance between method. Now, I'm going to jump over to Eclipse to show you this application, but I'm conscious of the fact that some of you in the room may be .NET or Swift developers, and I'm showing you Java code here. You may be offended by that, but there's not to worry, because we actually have a common design strategy across the runtime SDKs. So regardless of whether you're writing .NET or Java or Swift code, for example, the methods and the class names that we use are exactly the same across the runtime SDK. And the order of the parameters will be the same as well. So just because you're looking at Java code here, it shouldn't concern you if you want to look at another runtime SDK. So with that, I'm going to jump over to a Java application, and I'm going to run it just so you can see what it does. And it's a blank screen, which is very exciting. So ideally, what I should be able to do here is see some data. Let's just see what's going on. I don't have a network connection. Right, let me just restart that application and hopefully we'll have some success. Otherwise, there we go. Right, okay, very slow tiles, but at least we've got some data coming in. So, it's the wrong sample. Okay, we're there. So what we have here is a base map, and every time I click on the map, I'm going to create a point. And when I've got 2 points, I'm going to work out what the distance is between those 2 points, and I'm displaying the result in the polygon here. So let's go and take a look at the code that we use to achieve that. Now what I could have done here is I could have just used the distance between method on the geometry engine. And that's actually very good at working out the distance between 2 points which are fairly close together. But imagine your 2 points were geographically separated. So one of the points was in London, another one was in Johannesburg, in different countries. The result that you'd get back from the distance between method wouldn't necessarily be that accurate because we're using a Mercator projection here. And you get distortion when you sort of go across great distances with this kind of projection. So the correct method to get an accurate distance over long distances is to use the distance geodetic method, into which I pass in the 2 points that I'm interested in, and this will give me the result back in a much more accurate way. So just go back to the slides. So general information for when you're working with these geometry dimension methods is that the results will come back in the unit of the spatial reference of the geometry that you're working with. So if you're working with a Mercator projection, as you would do for the majority of the base maps you work with from ArcGIS Online, the unit of measure will be meters. And obviously all the geometries that you're working with, where you're passing in 2 geometries, they all have to be in the same spatial reference. But if they're not, well, we've got a method for sorting that out too. So we have a method to project between spatial references. So you may have a point that you're getting back from a Web Mercator map, but you actually want to work in a local coordinate system, like one of the US systems, or perhaps a local coordinate system for Great Britain, the OS Ordnance Survey Grid Reference System. And to do the conversion, you just need to call the project method. So let's go and take a look at this in an application. So if I just try to run the right one this time. So I start an application up here, and what I'm looking at is a Mercator map of the United Kingdom. So I'm going to click here, somewhere close to where I live, and what I'm doing is I'm actually using the project method to convert that into the local coordinate system that I'm interested in. So I'm showing in the label here the X and the Y coordinates of the local coordinate system. Let's go and take a look at the application here. So there's a few steps I had to go through to actually create that result. So the first thing I was doing is I was listening into a click event in my map view, and that was returning a set of screen coordinates. So this is like a coordinate measured in the number of pixels from the corner of the map view, and that's not particularly useful for me. So what I need to do is use the screen to location method in order to be able to get the geographic location back. So this is the Web Mercator, the Mercator projection point. And then I display that as a graphic on the map. And because I want to convert that into my local coordinate system, I've got a method here which I'm calling to convert it into the OSGB coordinates. So if we look at here, I'm using the geometry engine project method. I'm passing in the Web Mercator point, and then I'm passing in the coordinate system that I want to convert that into, which returns my projected geometry. And then I'm just displaying that in my mapping application. Now, it's also worth noting that when we call the project method, Internally, we have some tables which will choose the most accurate transformation for the area of the Earth that you're in at that particular point in time. But it may be that you want to be able to choose your own transformation technique. In which case there is a sort of a third parameter overload to this project method where you can specify a transformation that you want to be able to use. So if you're an expert on transformations and you feel there's a better one for the application you're writing with, then you can choose your own. Otherwise, the projection engine does what we believe to be a pretty good job of that. So the next group of functionality I want to talk around allows us to be able to answer spatial questions about geometries. So this is where you might want to say, is one geometry contained within another? Do they cross? Do they intersect each other? What's the nearest vertex along the line from this particular point that I've got? Do they overlap? Do they touch? Is one entirely contained within another? The example I'm going to show you here actually checks to see whether geometries actually cross. So if I just go over to another application I've written here, and if I start that up, I'm starting off here with a very uninteresting polygon, and I'm going to specify line. And I'm going to check to see whether they cross. Now, if they do cross, if they don't cross, I'm going to render the polygon red, but if they do cross, I'm going to render it green, like so. So let's go and take a look at the code that we use to do that calculation. It's very simple. So I was just using the geometry engine crosses method, and I'm passing in the geometry for the line and the polygon, and that's actually returning a Boolean value. And then I'm then using the Boolean value to be able to set the fill symbol of the polygon to make it green if it crosses or red if it doesn't. So it's very straightforward. So the third group of functionality I want to talk about is around creating geometries based on other geometries. Probably the most common one I see used is the buffer operation. So this is where you can take in a point and you can pass in a radius, and it'll create you a buffer or a circle like we've got here. So there are other ones. So there is union, intersects, and difference. And it's actually quite powerful, these, because you can actually build them up. So you can take the results from one operation and sort of feed them into another. So I've demonstrated this here. So this is an application I've written where I've got two red dots here, which represent the location of some low-powered radio transmitters. And the buffer operation I've created here represents the area where I can get a useful signal from these particular radio transmitters. And then I've actually taken that a step further. So I've performed an intersection operation of the two buffers, which represent the results represented in the blue area here, which will give me the strongest combined radio signals I'm going to get from those two different radio transmitters. So it's a very simplistic demonstration here, just showing you how you can build the results up. There's many more operations inside the geometry engine. I just go in and take a look at the user documentation. This is one I particularly like, actually. So you'll notice when I was working out the distance between these 2 points here, I was able to label a polygon with the results. So I actually used a method on the geometry engine called label point, passing in the polygon, and that actually gave me a point where I could actually anchor a label where it would sort of optimally render for that particular polygon. So that's just another example of a use for the geometry engine. So with that, I'll hand you back to Mike, who will talk about geoprocessing.
Okay, thanks, Mark. That was an excellent overview of using the geometry engine to perform, build up analytical operations on individual geometries. And those geometries could come from queries on your feature layer, or they could come from graphics within the graphics overlays. What we'll take a look at now is geoprocessing. And one actual difference between the geometry engine and geoprocessing is that geoprocessing typically acts at the level of a layer or an entire data set in contrast to the geometry engine, which acts on individual geometries that you pass to that engine. So geoprocessing is it's a framework and tools within ArcGIS, within the entire ArcGIS platform for processing spatial data. So it involves both analysis, spatial analysis, perhaps buffering a point, performing an intersect between two data sets, or running a viewshed on a data set. It also contains lots of tools for performing data management operations as well. Creating data from scratch, creating databases, creating feature classes within those databases, adding fields to them, setting domains on a field as well. So there's a whole range of spatial analysis and data management operations that you can perform there. You heard on stage on Tuesday morning, Jim McKinney said we've got over 1,200 tools now within the ArcGIS platform for geoprocessing. And the really great thing about the framework is it allows you to combine these tools into an entire workflow. So essentially you create a custom tool or a custom workflow by combining multiple tools together. So the output from one forms the input to another tool, and then you might split those and perform some processing or some iteration on those data sets. And there's two ways to do that within ArcGIS. One is Model Builder. So that's a visual canvas within ArcMap or ArcGIS Pro. And that allows you to drag and drop tools onto the window and then connect those together and set various properties. You can also use Python to essentially write the same functionality. And in fact, in many cases, people prefer to use Python because it provides a little more control over a lot of the properties and the flow of the script. And also they prefer it from the kind of documentation point of view as well. So essentially you create these tools, and then you can use those obviously within the desktop environment, which is where you do your authoring or you create these custom tools, and then you publish them to ArcGIS Enterprise, and that creates a REST endpoint onto that service. So your entire custom workflow is represented as a REST endpoint with the parameters that you defined and the output parameters that you defined. The ArcGIS runtime, whether we're talking about .NET, Java, Qt, or macOS, iOS, they all access those the geoprocessing functionality via those services. So you're calling from the API into that REST service. The execution happens on the server, and then it returns the results back to you in the API. So ArcGIS Desktop is your designer authoring environment for these custom tools, and then you can consume them within the ArcGIS runtime via services. So just a couple of screenshots there. So the ArcGIS tools are just the regular built-in tools that you see within Arc Toolbox in ArcMap or Pro, Clip being an example there. And then custom tools are just tools that you build up within Model Builder or within Python. So how do you publish geoprocessing services then? Well, the first step is to obviously design and build your custom script or model, and then you have to run that within ArcGIS Desktop. And what that does is essentially validates all of the inputs, it validates the entire processing of the model, and you get a set of valid outputs at the other end. And then that result that is available to you within ArcMap or Pro, you can then publish as a service to ArcGIS Enterprise, and it's essentially publishing that result. And the result includes the input data, the output data, and any project data that was referenced by that processing. So that's something to bear in mind. We'll cover some tips at in a few slides' time about how to optimize your workflows when building up these custom tools. And the fact that the input data, the output data, and any project data gets included within that result when it's published to the server is obviously a consideration based on the volume of data that you're running on. And then the ArcGIS Runtime API provides types, classes, methods to represent the geoprocessing service. It gets represented as a task within the API, and then specific requests to run instances of that task are considered jobs within the API. So the API has tasks which represent the service, and then jobs which represent specific executions of that service. And then the API has types to build up the parameters that you send to that service, and obviously the processing is done on the server side, and you get results back, and there are types to represent the results. So I talked there about ArcGIS Enterprise, and that assumes that your ArcGIS Runtime application is operating in a connected environment. You've got access to the internet or your local network where you're accessing that GIS server. But ArcGIS Runtime also supports local geoprocessing services as well. And this is one area where there is some differentiation between the SDKs. So if you're using the .NET SDK and you're building WPF applications, or if you're using the Java SDK or using the Qt SDK and you're working in C++, then there's a additional component available to you with the ArcGIS Runtime called the local server. And essentially this is like a mini GIS server, mini ArcGIS server, and that can host and run geoprocessing services. We don't support the full kind of 1,200 plus tools that are available. We've currently support about 300 tools, and there's an entire list in the guide documentation for the 3 SDKs that I mentioned, covering that list of tools. We essentially add tools to that list now based on what you ask us to add. So if you're looking at that list and there's something missing that you need to deploy in an application, please submit a request either via support or contact us on GeoNet or ArcGIS Ideas, and we can look at adding those tools to the local server. In order to create a service that's going to run within the local server, you need to package the result. So once you've run the processing within ArcMap, you get a geoprocessing result. You package that as a geoprocessing package, so it takes that input data, the project data, the output data, packages it together into a GPK file, and then you can deploy that with your application or provision it to your device somehow and then run that within via the ArcGIS Runtime API. One thing to note is the local server, the Runtime Local Server API includes essentially a mini administration API as well. You're responsible as the developer for starting and stopping these local services and controlling their life cycle within the application. So to summarize that workflow then, you create custom tools within Model Builder or within Python, within ArcMap or ArcGIS Pro. Use that to create either a geoprocessing package to use within the local server or as a service definition to publish to ArcGIS Enterprise. And then you access those services via the ArcGIS Runtime API. So let's look at some tips then. I've mentioned a couple of times that when you're running that processing in the desktop environment, that the result contains the input data, the project data, and the output data as well. And that's what gets bundled into the service definition that gets uploaded to your enterprise server or gets included within that GPK file. So that's a consideration when you're running that script or model for the result that you're going to publish as a package. You should keep the input data small and make sure that the result output data is going to be pretty small as well. And maybe even consider subsetting the project data that's going to be accessed during the execution of the model, so to keep that overall package quite small. You should, wherever possible, use data that's local to ArcGIS server itself or the local server. It is possible to pass into these custom models. You could pass a string that's a path, for example, and for the local server that could be a local path on disk. I suppose it could be a network share, but then obviously you're going to incur the overhead of reaching out and pulling data across the network. If you, wherever possible, write data to the in-memory workspace. So you can write data to file geodatabase, shapefile, raster data. There's actually an in-memory workspace that you can write to, which is more efficient and doesn't incur that disk I/O. Any data that you're using should have, as with in most cases actually, should have attribute and spatial indexes. Spatial indexes obviously pretty vital actually to most of the spatial data that you're working with, but any queries that you're doing on attributes, those fields should have indexes as well. Think about what coordinate systems your data is in, so avoid any unnecessary coordinate transformations within the model or within your script. That's just an extra overhead. And reduce the data size wherever you can. Consider subsetting the data depending on what the user workflow is. And you will find a lot of those tips in the ArcGIS Server Help under Performance Tips for Geoprocessing Services. And those apply whether you're publishing a service to ArcGIS Server or whether you're creating a GPK that you're going to use with the ArcGIS Runtime Local Server. It's essentially exactly the same concepts. Okay, so let's take a look at a demo now of geoprocessing. So the first thing that I'll do actually is just run the application and we can see what it does. So the blue box is just highlighting my area of interest here. I've got one of the Esri base maps in the background. And what I'm going to do is define a line across here, and that's running an elevation profile. I see, okay. All right. Okay, so what you're looking at now is a WPF application. The blue box is the area of interest. There's the world topographic base map in the background. And when I define this line across Palm Springs there, it's calling out to a local geoprocessing service, running an elevation profile, and then returns the geometry. And then I'm using some WPF charting components just to chart that on the line here. And actually, if I hover over the chart, you can see for that particular point, I know exactly how far it is from the start of the line, and also I know what the altitude is as well. So let's take a look at how I did that. Well, the first thing that I did is get the data that I want to use in my analysis. So I've got an extract of some elevation data here, and then I wrote a Python script, which I'm looking at in Notepad here, but you could use a number of different Python IDEs. Visual Studio is actually particularly good for building up your Python scripts and debugging those. So in the script here, I import a couple of namespaces. I get the input line that's been digitized. I also get the raster. So I'm going to expose a parameter that is just the string to a path for a raster file, so I can provide that at runtime to the service. And then I'm using the in-memory workspace that I'm going to hold a couple of geometries in temporarily. So I run the 3D Analyst interpolate shape command based on the elevation data and the input line, and then the output shape Z is my line that gets interpolated across that terrain. What that does is add a Z value to each of the vertices of the line. And then I run another ArcPy command called create routes or create routes within the linear referencing toolbox, and that adds the measure value onto each of those vertices as well, so the distance along the line. So that's how I was able to hover over the chart and get both the Z value and the M value. And then I simply set the output geometry, the output shape M, as a parameter that I can retrieve via the API after the execution of the model. So having written my Python script, the next thing to do is add that Python script to a toolbox that I've done here. I've created an interpolate shape toolbox, added the script to that. I've added the raster data to the view here. ArcMap auto-generates the UI for that. So one thing that I had to do actually is in the process of adding the Python script to the toolbox here, if we take a look at the properties, there's the source, which is my Python script on disk. The other thing that I had to do is define the parameters. So define the input lines as a type feature set, define my input raster as a raster data set, and then the output profile as a feature layer. And you can see for the third one that the properties of that is a derived out, and the direction is output, and it's a derived type. The other two are input types. So based on those parameters that I've specified, ArcMap's able to auto-generate the UI, and it's requesting two things. Obviously the line that we talked about, so if I define that line across there, and then it wants the path to a raster file, so if I drag that from the table of contents and run that, and that's now running within the context of ArcMap, so just running that elevation, and then we get the line here. And if I open up the attribute table of that, you can see that it's one line, but it's a polyline with Z and M values. So it's added the Z values as it's interpolated the line across the terrain, and it's added M values from running the linear referencing command. And then if I look at the geoprocessing results window, we can see within my current session, I've got a successful execution of the interpolate shape model. And if I expand that, check the messages, we can see it succeeded. And the process for running it within my WPF application, what I want to do is share it as a geoprocessing package. If I wanted to publish this to ArcGIS Server, then I would choose service type there. So publishing as a geoprocessing package, one of the important things that you need to do is check this box to support the ArcGIS runtime. And that essentially creates a toolbox service definition file within the geoprocessing package. And then it's a case of filling in some additional properties in here, the name, description. I get some control over the input types as well. In this case, I want the input line features to be a user-defined value, the input raster to be a user-defined value. If I wanted to choose a constant value and include that raster dataset as an input, I could choose that as well. And then the output profile is the output derived line at the end. And then it's just a case of sharing it as a geoprocessing package file. And then within Visual Studio here, we can see that I've got some code here to start a local geoprocessing service. And that references that interpolate shape GPK file that I would have created. And I said that some of the API features in here are like a local server admin. So that local geoprocessing service creation is kind of a mini server admin role. I set the maximum records that are returned from that. If you're familiar with any of the server administration, that's a property of services generally. And then also I choose the service geoprocessing service execution type here. So I know that this tool on this level of data or this volume of data will execute quite quickly. So I've chosen the synchronous execution type. That essentially determines the kind of infrastructure that's spun up around that local geoprocessing service. I get one service, I submit the request to it, it executes, and then it returns either a failure or a result. There's another type which is an asynchronous submit type, and it spins up an extra service which is kind of a monitoring service and allows me to request updates during the service execution, so I can determine how the execution is processing. And there's kind of a guideline if you would probably want to choose the asynchronous submit type if your model or script is going to run for more than a few seconds. You want to provide some feedback to the user, visual feedback within the application of how the processing's going. And then I start the service. I create a geoprocessing task there. So that's based on the URL plus the task name. And then the rest of the code here is request using the sketch editor within the UI to request a line that I digitize across the terrain, verifying the geometry, adding some graphics to the display. I'm actually doing a projection of the geometry there. So I'm using the geometry engine that Mark talked about within the context of submitting data to my geoprocessing operation, because I know that the user-drawn geometry is coming in the spatial reference of the map view, which in this case is Web Mercator, but I know that my elevation data set is in the Miller projected coordinate system. So I just need to project my data between those two coordinate systems and then build up the parameters. I want to return both M values and Z values, and that again allows me to display that WPF charting component with the M and the Z. I'm setting the output spatial references Web Mercator, but the processing spatial reference is that Miller spatial reference that we reproject to the feature to. And then building up the input, which is a feature collection table. So this is just an in-memory collection of features. So I'm creating a new field, adding an identifier field to that, passing in my polyline, set those following lines of code, just set that feature on there. And then there's eventually down here, I'm asking the geoprocessing task, which represents the service, to create a new job. And then by calling the getResultAsync method, this is kind of a convenience method really. It just starts that job and then waits for the result. So I'm using asynchronous features of the API here, the await, to await that job result while it executes. and then I get the result back, and then there's some validation there. So if there was an error, then it would have said, yikes, there's no elevation here. Otherwise, I iterate the parts and the points within that line, and I build up my resulting line to hand back to the UI to display into the charting component. And essentially, I just bind onto the item source for the chart line onto this collection of points that I'm building up. And that's how, in the result, we get the ability to hover over that terrain. And you can see actually the execution within the local service is incredibly quick, returning that result very quickly. So that was a demonstration of creating a Python script to perform some analysis, running that within ArcMap on the data, sharing the result as a geoprocessing package, and then using that geoprocessing package within an application, making use of the geometry engine actually to perform a projection of some data as an interim step or intermediate step, and then executing that and presenting the results in an application. All right, now I'd like to hand back over to Lucas, who's going to take a look at visual analysis within the ArcGIS runtime.
All right. Okay, so I'm going to talk about visual analysis, which I think is oftentimes not thought of initially. You know, we think of geometry manipulations, we think of geoprocessing in ArcGIS, but throughout the conference so far, up on the plenary, you see all the cool things like insights, and really that's doing visual analysis. So you can use visual analysis to visually detect patterns, trends, and outliers in your data, and you can build nice user experiences into your applications so that you can actually discover information about your data that you might not have known before. The key things to know are that it's really different from GP and geometry engine because you're not really giving it explicit inputs and getting explicit outputs as much as you are really exploring your data. So think about a heat map renderer in ArcGIS Online versus using one of the kriging tools in Spatial Analyst in desktop. They give you a similar output in the sense that you're interpolating points and getting a surface, but the heat map render is really meant for a quick reference. You quickly see where crimes are centralized in a city, for example, whereas kriging is really meant for more of a conclusive analysis. You can perform visual analysis on both vector and raster data and in 2D and 3D space. So the first thing I want to talk about for visual analysis is what we're calling exploratory 3D visual analysis. And this is something that's brand new with 100.2, the update 2 release of ArcGIS Runtime. We have two types of analyses that we support currently. We have line of sight and we have viewshed. These are very fast performing analyses because they're GPU driven. The results are displayed on the scene and you don't get anything back to persist. So this is where it really differs from Mike's demonstration. You could, for example, with geoprocessing, run the viewshed tool, create a geoprocessing package, get results back and display. That's one way to do it, but with these new visual analyses, you can actually just drop a point and the output result displays on the screen. Another thing to note is that the output acts on the current resolution of the data. So if you're zoomed out very far and you want to perform a viewshed, it's going to have some pretty coarse-grained data, whereas with geoprocessing, it's usually acting always on the finest grained detail of the data. If you zoom in and perform the viewshed again, you'll probably get different results than when you're zoomed out further. And that's because oftentimes the elevation surfaces that you're working with are tiled in levels of detail. So as you zoom in, you get greater and greater detail. All right, so what is line of sight? We've seen it in the plenary session if you were there, but the concept is demonstrated in the image in the bottom right of this slide. Consider that you have two different points, what we call a target and an observer, and you want to see which parts of an imaginary line between those 2 points are visible. So in this case, you have a green graphic at the top of the building, and then you have a red graphic down on the ground. And part of that line is visible, but the rest of it is obstructed by the building. So if that red graphic were to move further towards the bottom of the screen, it would eventually become visible. So there's two varieties of line of sight that we support in the runtime. We have location line of sight and geo-element line of sight. Location line of sight basically takes 2 point geometry objects in the constructor. So you set point A and point B and perform the analysis, and it will display between those 2 points. Now, geo-element line of sight is the same principle, but instead of giving it geometry objects, you give it geo-elements. In runtime, geo-elements are the base class for graphics and features. So you could obtain a feature from a shapefile or from a feature service, or you could just programmatically create graphics and pass those in. So then the nice thing about this is that you can actually hook to graphics, and if those graphics geometry change, the analysis will automatically update. So picture you have a car driving through a city like we saw in the plenary session. There's a car moving through. As that geometry changes, the analysis is automatically updated and displayed without you having to do anything as a developer. We also have events that are triggered when the target becomes visible. So if that red graphic began to move towards the bottom of the screen and it became visible, we would get an event raised, and we could let the user know that now the line of sight is visible. So here's some C++ code of what that would look like. This is using the location line of sight. So I'm creating 2 point objects, the observer and the target. Next, I'm creating the location line of sight and passing the observer and target points in. Next thing I'm doing is I'm appending this to an analysis overlay. An analysis overlay is very similar to a graphics overlay. Graphics overlay display graphics in the map or scene. Analysis overlay displays analysis results in the screen, or on the scene. So passing that in will automatically update any changes that I make to the location line of sight. Then the last couple of lines here, I'm just setting some additional parameters. I'm setting the color for the visible and the obstructed parts of the line, and I'm also changing the output line width. So viewshed is very similar to line of sight, but instead of having a line between 2 points, you have 1 point and then the output is a raster. So in this case here, you can see there's this blue frustum outline that I have that represents my observer location, and the output is this raster over the scene. The green parts, again, are the visible parts, and the red parts are obstructed. There are 3 different varieties of viewshed that you can perform. Location viewshed with a camera, location viewshed with a point, and the geo-element viewshed. So this follows the same paradigm as the line of sight. Location viewshed with a camera takes a camera object in, and camera is how we refer to your current viewpoint in a scene. So as you go through a scene, you have your X, Y, and Z for your current location. You also have your heading, which is the direction you're facing, and your pitch, which is your up and down angle. So all of these things make up your camera. So you can set a camera object, perform the viewshed based on that camera. You can also just give it a point geometry. If you give it a point geometry, you have to set some additional things like the heading and the pitch. And finally, you can use geo-element as well. So this works in the same way as line of sight. You can give it a graphic or feature, and then if that graphic or feature's geometry changes, the viewshed will automatically update. So here's some code showing the location viewshed. I have a function here that takes screen coordinates in, and then it's using screen to base surface to get a point. And then next I'm creating a location viewshed, passing that point in, setting some additional parameters like the heading, pitch, horizontal and vertical angles, and then the minimum and maximum distance. Appending that to my analysis overlay will then display the results in that overlay. All right, so let's see these in action. So here I am in our Qt sample viewer, but all of the SDKs have these samples available to you. So this is in Patagonia, and I have an observer towards the top of the screen and then a target currently at the bottom part of this line. And as I click, the line of sight is updated. So now we're going to the Alps, and this demonstrates viewshed. When I click, it drops a point. So this is using the location line of sight that takes a point geometry. And then I have a panel here that allows me to change some of the parameters. So I can do things like change the horizontal angle, change the heading, and change the pitch. So this frustum outline is the blue lines here, and that helps you visualize what your field of view is. So you can see as I move around that it's very fast to perform, so that demonstrates its performance. Finally, I'll show you viewshed with a geo element. So in this case, I have a scene layer with some buildings. And I'll zoom in here. I have a model here. And as I've set it up so that when I click, this is a graphic. So as I click, the graphic's geometry moves slowly towards where I clicked on the screen. And as I click, as it moves, the viewshed is automatically updated and displayed. You'll see a few discrepancies, like right in front of it right now, it's red, and that's really because the data has slight changes. So actually, even though right now it doesn't look obstructed, if you were actually go and zoom in at the exact angle of the graphic, it would be not visible. Okay. So now we'll move on to other forms of visualization, which are more traditional, and some of the things that we've had in the runtime for a little bit now. When you're visualizing vector data, you can use symbols and renders to change how your map looks depending on attribute data values. So this is the type of thing that you see with insights and smart mapping, and where you can really start to explore the data that's on your map. So you can use things like unique value render and class breaks render to really make some of the information that's inside of your data pop. For example, with unique value render, you can display a different symbol per unique attribute value. So maybe you want to look at a city's favorite sports team and map that out and see where people's allegiance lies. Or maybe with class breaks render, you want to display different symbols for each attribute in a range of values. So you could look at things like median income, for example. Smart mapping renders bring more and more functionality in because traditional renders, typically you're displaying things based on one attribute value or one field. But now with smart mapping, it's built on this concept of what we call visual variables. And with visual variables, you can display multiple attributes. So for example, you could have one symbol that changes color, transparency, rotation, and size. So you can have potentially 4 different things that you're mapping at once, which is pretty cool. Now we also have raster renders. They work in a similar way. We have the hillshade render, blend render, stretch render, RGB render, and color map render. I think hillshade render really lends itself to analysis because you can answer lots of common questions like where would the best place to be to plant a garden, or if you were to put up a new building in a cityscape, how would that affect the shadows on the rest of the city? So for that, I'm going to show another quick demo. So this is showing a DEM in Hawaii, and it's just placed over top of some imagery. And as I click, it moves the sun, and the sun updates the azimuth. And so you can see what the hillshade effect will be based on the azimuth, so you can get an idea of what it's like different parts of the day. This is all performed on the client, so it's very fast, as you see. So you can think of different scenarios. For example, you might be the Park Service looking at potential rescue operations and consider which parts of the terrain are going to be shaded during different parts of the day. And you can also do things like apply the blend renderer to also add elevation into it. So all of these things help you visualize the data just a little bit better than the plain DEM. Okay, and with that, we'll pass it back to Mike.
Excellent, thanks, Lucas. So in those series of slides and demos, you've seen a range of different types of analysis that you can do with the ArcGIS Runtime. So individual geometry-based analysis with the geometry engine, modeling custom workflows with geoprocessing. We've taken a look at different variety of visual analysis as well. So now we'll just wrap up and take a look at the roadmap, what we've got planned for the future in terms of analysis. So actually the first thing that I thought was interesting, this is the slide that we presented last year for, actually sorry, this is the summary slide, it's the next one. So the ArcGIS Runtime provides a variety of different ways to enable analysis in your application. One thing that we've tried to show during this as well is that it's common to combine these different workflows. So in the geoprocessing example, I use both geoprocessing and geometry engine to achieve my result. That analysis in many cases is local to the device. So we've got that high performance, you saw in a variety of examples there, really high performance analysis running on the GPU or CPU on the device. But then also the ability to call out to services where they're exposed and run analysis on the server as well. So in terms of the roadmap then for analysis within the runtime, this slide was one that we presented in 2017 as the roadmap for analysis in 2017. And actually we delivered all of these features, I think. So we added some additional tools to the local server. We added about 20 tools to the local server across some analysis, but more data management tools. And then those were basically based on customer requests. So anything that you ask for, we can take a look at adding to the local server. In some cases, it's not possible due to the framework or the requirements that some of those tools bring with them. But in a lot of cases, it's actually as simple as just us adding another DLL to the local server and then making sure that's built for the appropriate architectures. We added renderers and additional support for smart mapping, so the visual variables that Lucas was talking about and the raster renderers. That's 3D on-the-fly analysis, so the line of sight and the viewshed running on the GPU there, high performance visual exploratory analysis, and then network analysis as well, so support for service areas and closest facility, both running off local data sets on the device, so again providing high performance transportation network analysis. So we managed to do all of that in 2017. Let's take a look at what we might be able to achieve in 2018 then. So we're again looking at what tools we can add to the ArcGIS Runtime Local Server. We're looking at what additional 3D exploratory analysis tools are required, such as 3D distance perhaps, or and then also the ArcGIS Runtime Local Server is going to see an enhancement. We're working on support for creating geoprocessing packages with ArcMap 10.6. So currently the current 100.2 release of the local server, you create packages with ArcMap 10.5.1. And then also we're looking at support for ArcGIS Pro packages, so creating a geoprocessing package within ArcGIS Pro, which would be a GPKX file, and then running that within the local server as well. So some really good enhancements across the core ArcGIS Runtime API and also local server as well. All right, so with that, we'll close the session. Thank you very much. If you've got any questions, we have some time now to take them.
Compared to ArcGIS, the analysis capabilities in the runtime, compared to the ArcGIS.
Okay, so the question is, how do the analysis capabilities compare with ArcObjects? So ArcObjects, you could use that to build custom applications with an ArcGIS engine, or you could extend ArcMap. The capabilities there, you can build your own, you can use the same geoprocessing capabilities that we have within the ArcGIS Runtime Local Server. In fact, there are Arc objects in the ArcGIS Runtime Local Server. You just can't get to them as an Arc Objects API. You run that, you execute that through the local geoprocessing services. One area that isn't in Arc Objects is support for some of these new renderer types, such as the visual variables and the smart mapping that we're seeing added to ArcGIS Online that we support visualization of within the runtime. And then also the that GPU-based real-time visual analysis tools as well weren't available within Arc Objects. So there's some support, some equivalent support, but then new features within the runtime as well. Okay, if there aren't any more questions, thank you very much for joining us this afternoon.